So it is my pleasure to introduce the next speaker of our first day. The next speaker is from Argentina, like myself. His name is Enzo Ferrante. He completed his PhD in computer science at Université Paris-Saclay in France and worked as a postdoctoral researcher at Imperial College London in the UK. He returned to Argentina in 2017, where he is currently a researcher in CONICET. He's also an AXA Research Fund Fellow and lecturer in digital image processing at Universidad Nacional del Litoral, working in the SYNC-I lab. His research interests span both artificial intelligence and biomedical image analysis with focus on deep learning methods. And he's going to tell us about convolutional neural networks and computer vision.
Thank you, Martin, for the introduction. Okay, hello everybody. I'm really happy to be here, and I want to start by saying a big thank you to the organizers of Khipu and for the invitation, but also for having this event here in Latin America. When I was an undergrad in Tandil many years ago in Argentina, before going for my PhD outside, I would have loved to have an event like this happening in Latin America, in Montevideo or wherever. So I think this is great. And so in this talk, we will talk about a really introductory talk about convolutional neural networks. Today, in the previous lectures, we had a talk about evaluation. Luciana was talking a lot about that. We had talk about optimization as well with René. And here, we will start talking about the models that we actually use to solve these problems. And I want to stress the fact that this is a really introductory lecture. So those of you that are experts in CNN can follow Guillermo's advice and go to the beach if you want. That was that way, I think. Okay, so I will start by defining a really basic concepts like computer vision tasks. I will talking a lot about computer vision tasks because convolutional neural networks have shown their maximum potential in these tasks, right? So I think these are prototypical examples where actually convolutional neural networks show to be really good at. So, for example, some of these tasks, like image classification, for example, this is the typical meme that we all love about chihuahuas and muffins, right? This is a problem where we have an image and we have to classify it in different categories. This is a really basic task, but we will talk a lot about it today. Another task like object detection, for example, is when we have to not only say which objects are there, but also put a bounding box there, localization. Also image segmentation. This is another one of the applications that we will see today, how we can solve using convolutional neural networks. In image segmentation, we have to produce pixel-level predictions, differently from image classification, where for every image, we have to only predict one class. Here, we will have to classify every pixel of this image in a different class. So actually, for the people that are not familiar with computer vision, maybe you are coming from an NLP background or another applications of artificial intelligence. When computers look at the images, what they see is basically a matrix of intensities. And our objective will be to generate a model that can tell us what's the probability or something close to a probability, according to Luciana's talk and what she was telling before. What's the probability of having a given class in this image? For example, having a cat here. So traditionally, this problem has been solved, and I think René was commenting briefly about this today in the morning. Following this paradigm, basically we have an image here, an image of a bike, and we want to say what is in that image, right? So what we could do, especially during the 90s, there was a lot of research about this, and the beginning of the century. Basically, what we will do at the beginning is to extract features from these images that can explain in a better way what is there, because it's not that simple for a computer to see the image and infer that, right? So we have a lot of different feature descriptors. I'm not going to enter into the details here, but just think about them as being features that can explain what is in the image in a better way than just the intensities, right? And with that, we construct a vector, perform some feature selection maybe to see which are the most discriminative features, and at the end, we plug these vectors into a classifier, your favorite classifier, wherever it is. And you have a prediction for that. But what's the problem with this? Well, the main problem is these features are handcrafted. And this word handcrafted, we use it a lot, but it's basically just saying they were designed to deal with a particular problem in these images. For example, I don't know, like hog, or looking at gradients of, histograms of gradients, sorry. Different descriptors that can help, but they are designed by hand. We specifically tell the computer how this feature is created. Now, this was good, but then deep learning came. And I really like this definition from the Nature paper of Jan LeCun, Benjo, and Hinton, the 3 Turing Awards researchers. And the nice thing about deep learning is that these representations, these features, are going to be now learned using multiple abstraction levels. But the interesting thing here is they are learned for the particular task we are trying to solve. René was saying that today in the morning as well. And so this changed completely. This produced a change of paradigm, I think, in the way we solve vision problems. And in this case, then, we will have something. We'll have our image now, but we will have something here that will learn different features in different abstraction levels, like going from low-level abstraction, like borders or simple shapes, going towards more complex parts. And this is how they look, using some visualization techniques here. And I will, at the end, say, OK, this is the class of the image. But the nice thing about it is that we are training together in an end-to-end way our feature structures and our classifiers, everything together in the same model. Now, the question is, what is in this model? What do we have there? Well, what we have there are our loved artificial neural networks, right? And René talked a little bit about this today, but just to recap, an artificial neural network is just a product, right, between an input and the weights that I will learn, and this will pass through a nonlinear function, and this is how a neuron looks, right? I have my input, I have my weights, the weights I'm going to learn, and I produce an output. Now, if I combine a lot of them, I come with something like MLP, multi-layer perceptron, that we already discussed before, about the universal approximation theorem and so on. So we have our function here. These are the parameters we are going to learn in MLP. But this is basically a mathematical function that takes inputs, parameters, and produce a prediction, right? When we are learning these parameters, we need something to guide this learning process, and this something is our loss function, right? For example, cross entropy, as we were discussing with Luciana before. And we use gradient descent to learn this. Well, this is when we have nice functions, but it's not happening in general. But the idea here is that we follow the opposite direction of the gradient of the loss function with respect to the weights that we want to learn. And the way it looks when you walk in this nice surface, but reality is not like this, as we were seeing in the morning. And we have these horrible things here, and we'll try to solve that. But well, there is a really nice paper that I think actually was there in the list of papers that René put in the morning. It's called The Loss Surfaces of Multilayer Networks. It's a paper by LeCun, actually. And some of the take-home messages from this paper is that, yeah, gradient descent does not guarantee to find global optimums in this horrible manifold, in this horrible surface. But for large-size networks, most local minima are equivalent and yield similar results when we go to test data, right? This is some of the things we were discussing before. And in general, also, just think about it. You train using some training data, right? So focusing a lot on finding the global optimum for this particular training data set may lead you to overfit. So if we don't get the global optimum for the training data, I mean, it's still OK, and we can perform pretty well in test data. And this is what we have seen. Now, this was kind of a recap for, and these are the frameworks, right? TensorFlow, PyTorch, and many others that you can use nowadays to implement these things in a really easy way. I think these frameworks have democratized the access to deep learning in general. Many people just using a couple of lines of code can today program their own neural networks. But this is really nice, but when it comes to images, that is the case I want to talk today, this is not that nice. Imagine I have an image of 100 by 100 pixels, right? If I want to process this image with an MLP, what I'm going to do is just to vectorize the image and plug it into the MLP, right? Now, let's think a little bit about the parameters. What happened with the parameters here? Here, I'm saying I have 1 million components in this vector, right? Because I vectorized the image. Now, if I plug it into an MLP, well, for a given neuron, I will have million weights, right? And if I do that, like for example, for 124 neurons in the first layer, I will be having a lot of parameters there. So this clearly doesn't scale, and we have to do something else to process these images. And this is where our convolutional neural networks come and help a lot. So disadvantages of processing these images with an MLP are basically, okay, not suitable for big images. We lose the original data structure because since we put them in like a vector, pixels that used to be neighbors that now they are not neighbors anymore. And there is no clear notion of multi-resolution analysis, which is a really useful notion when we are trying to understand images, right? Looking at the image at different resolutions. So it wasn't in that moment when we started to think about neural networks that are inspired by the human visual system or the mammals in general. And let's do a little bit of history here and go back until '62 when Hubel and Wiesel published this paper, which actually gave them the Nobel Prize of Medicine, I guess, for these and other works. And what they did in this experiment was the following. They had a cat, and they inserted an electrode in the visual cortex of the cat, so the area of the brain that is related to processing visual stimulus. And they started to show different patterns to that cat, different patterns in different orientations. And what they saw there, after doing this experiment, was that the neurons that were in the early layers of our visual cortex started to react to simple patterns, while the neurons that were later, before in this cascade, let's say, of neurons, started to react to more complex patterns. And this is something similar what we have seen before, right? What I was discussing with you at the beginning, this idea of composing patterns. And this, another of the important conclusions of this paper was that in the proposed models, the neurons that are in the later layers have bigger receptive field and are less sensitive to stimulus position. And what does it mean? What is the receptive field of a neuron? Well, this is a really important concept when talking about neural networks, and this is basically the area of the image that will affect the output of the neuron. This is the receptive field of it, right? If one of my neurons is firing some value and I move something here and that value changes, well, this is affecting the receptive field of that neuron. This is part of the receptive field. That was in the year '62. Now, in the '80s, there was this interesting paper by Fukushima where they proposed the first artificial neural network that looked kind of very similar to this model we were discussing before. And this was the neocognitron. In this model, he showed something like a hierarchical relation between the neurons. And I think this image is also from the paper, and it's really interesting because it shows really well what the receptive field is. So this neuron is looking at this particular part of the image, but the neurons that are in the later layers are combining information from previous one and composing and looking at more complex patterns and reacting to them. So that was published in the '80s. And in '98, it was when Jan LeCun published his paper about gradient-based learning applied to document recognition, the paper where he published for the first convolutional neural network that actually was used to classify digital manuscripts. And in this paper, so the definition of what is a convolutional neural network then is basically any neural network that has a convolutional layer in some part. This is the definition that Ian Goodfellow is giving in his book. So now we need to talk about a convolution. What is a convolution? So mathematically, and for people coming from electrical engineering or signal processing backgrounds, they will be really familiar with this definition. The convolution is the integral of the product between two functions, right? A function x and a translated and flipped version of another function. Here, this is my input signal, and this is my filter, and the result of this integral is the convolved signal. And it looks something like that. This is the filter I'm applying if I'm in 1D, right? This is the filter I'm applying, this is my original signal, and this is the resulting convolution signal. This is in 1D. Now, okay, and this is the operation we use, the symbol we use to describe the operation. This is in 1D in the continuous case, but when we go to the discrete case, then it's just replacing the integral with the summatory. And then in 2D, we just add another dimension and another index, right? This is the definition of convolution then. Something that is important to know is that convolution, as I was telling you, is flipping one of the signals. But in general, what we use is not convolution, but correlation, where we replace this minus by a plus in this case, right? And this is what many of the frameworks we use are implementing, actually. But well, we call them convolutional neural networks because, I don't know, because of marketing, maybe because it's a nice name, I don't know. It's a more fancy name. Okay, and this is how it looks, a 1D convolution here, right? So I have my signal, and this is a discrete one. And what I'm doing is basically doing the product between every one of these elements with the other one and summing this, and putting it here as the output. And then I move the filter, and I do the same. And I move the filter, and I do the same. This is 1D. This is 2D. Yeah? So I just convolve here in the spatial dimensions. So with this definition of convolution, now I can go and create a convolutional layer. So how does it look, a convolutional layer, when I'm processing an image? Well, it looks like this. What I have is my input image here, which in this case does not only have height and weight, but also it has channels. So imagine an image that is RGB, for example, you have 3 channels. If I'm dealing with medical images, for example, which is actually the domain in which I apply most of the methods I develop, I can have many more. I can have different sequences of magnetic resonance images. I can have different type of informations. And these are all channels. And when I process them with my convolutional layer, what I do is actually, I take a filter, and this is what I'm going to learn. You remember that in MLP, what I was learning were these weights that I multiply with the input or any of the other layers. Here, what I learn is basically this kernel, this convolutional kernel. And the kernel is convolved in a space, but it's fully connected in depth. So it means it will have as many elements here in this matrix as I have in the channels, in the input channel. And whenever you use, you implement one of these, it's okay? What you have to say is how many, for example, output feature maps you want. So a feature map is the output of a given, after I apply one convolutional layer, what it's the output of it, it's called a feature map. Because it's not an image anymore, because this image was transformed in something else. I extracted some features from it. So, for example, if I want to have 2 feature maps as output in one layer, well, I will have to learn 2 different kernels here, okay? And this is something important, because this is actually the parameters I'm learning. And more importantly, the convolutional neural networks implement something called weight sharing. So weight sharing is this idea that I will use the same kernel to process all the image. And thus, this fact reduced the number of parameters drastically. Because before, if I had to connect one neuron to every element here, it will take a lot of parameters. But now, I have only this small kernel, and I reuse it along all the complete image, right? And this is great, because it also gives me some translation invariance, in the sense that, imagine I have a kernel that reacts to, I don't know, circles or to cats, and I'm looking for cats in the image. I don't care where the cat is in the image. I just care about the fact that an activation, that the kernel is giving a high activation because it found the cat. So since I'm using it in all the image, it's going to be OK, and this introduces translation invariance. And then I also use nonlinear activation functions, as we did in MLP, but these nonlinear activation functions will be used element-wise as in the outputs of every element in my feature map. So this is how it looks, one convolution applied to an image, and this is the feature map I'm obtaining when I'm using different filters here. So just to know what time is it? Okay, I'm doing fast. Okay. So as I was telling before, if I want to learn like one convolutional kernel, I will have only one feature map. If I'm learning two convolutional kernels, I will have two feature maps, and so on. So what are the parameters I have to specify when I define a convolutional layer? Let's say I have an input image that is 5 by 5. That's the size of the input image. So one thing I can do is to use padding. Padding is basically adding some data, and you have different ways of doing padding in a convolutional when you implement a convolutional layer. But let's say here I'm doing zero padding, just adding zeros around it. I could do like mirroring or other operations, circular, whatever. So this is padding, and basically in this case I'm doing padding of 1. Then I also have to define what is the size of the kernel, of the convolutional kernel I'm going to use, right? And this in this case is 3. Another thing that I need to define, and these are all parameters that you're going to put in your network. I think in the afternoon you have a practical session on convolutional neural networks. So some of these concepts, for sure, you will use them when you go to that class and try to implement it by yourself. So stride is basically telling me how many elements I'm jumping when I'm moving my window, right? So in this case, it's stride of 1. And this will give an output. The output of that image is going to be determined by all of these elements, basically. So I will have the input size, the filter size, the padding I'm using, and the stride. And this will give me the output size. When you are implementing your own architecture and creating your own architecture, you have to do the numbers to see how the images are flowing through it, right? And what is the size of the feature maps, and so that you can be sure that all these sizes matching with the other ones. Okay, so that's why I think it's really important to know the things. So in this case, I'm using one padding here just to be sure that the output of the convolution has the same size than the input, and this is sometimes really useful. This is what would happen, for example, if I don't do padding, I would get an output that is smaller than the input, right? Okay, which other layers do I have in a convolutional neural network? Well, I may use also max pooling. This is a really important layer. Pooling, something that is important to know about is that there is no parameter to be learned in a max pooling layer or whatever pooling layer I'm using here. So the idea of max pooling is really simple. I will just take, if I'm doing, for example, max pooling with a 2 by 2 kernel and using a stride of 2, so jumping every 2 elements, what I'm going to do is to take the maximum activation of every one of these windows and take this value here. And this also helps to introduce translation invariance, because I don't care, again, where is the activation coming from. I just know that there is an activation coming from some area from there, and will help to introduce translation invariance to my network. So another type of pooling that you can use is also sometimes average pooling. Well, there are different things that you can do here. And finally, another element that you need is sometimes fully connected layers, right? That are basically putting an MLP, and you use it in the end of the network in general. Now we are going to see it. But I can combine all these three layers, these three type of layers, to construct my convolutional neural networks. And this is the convolutional neural network proposed by LeCun in 1998. It's called the LeNet. And here you had convolutions, subsamplings, convolutions, subsampling, and fully connected layers. So what's the nice thing about it is that this part here, the part where I'm doing convolution and subsampling, is going to learn the features. This is the part of the network that is going to learn the features. And the other one is the part that is going to learn to classify these features in different classes. So one last element that we need usually at the end is, let's say here I have a 2-class or 3-class probability, like classification problem. So I will have 3 outputs here, and what I'm going to use is a softmax function to give this probabilistic interpretation of the output, right? And the softmax function is a function that basically takes your vector of outputs. These are the 3 outputs from my neural network. And if I plug them in the softmax function, I will get something that is all positive and sums to 1. But as Luciana was discussing before, this is not calibrated. And if we want to really interpret it as probabilities, then we have to do a little bit more of work. So these are convolutional neural networks. And they have many advantages when processing images because they are adapted to the regular structure of the images, right? If I'm processing an image with a filter, I know that, for example, 2 pixels that are neighbor in the image, they are supposed to share some kind of information because they are close. And in real life, if 2 pixels are close, they may be related to the same object or have something in common. So this is why this is really suitable for images. Well, translation invariance, as I have told you, end-to-end learning, this mechanism of weight sharing that helps to reduce the number of parameters. And they are really efficient in test time. And this is really important as well. It may take a week to train a convolutional neural network, but when we go to test time, the only thing we have to do is to pass it through the network, right? And I will get a prediction. And this is really fast, and even faster if I do it in GPU. So that they are really efficient in test time. And actually, we have some networks nowadays that are deployed in mobile phones, or I can actually compress networks and then put them in mobile phones and whatever. And they have good generalization when trained with enough data. What enough data means is a big question, right? And this is, it depends on the problem we are dealing with. In ImageNet, enough data means having 1 million images. In medical imaging, we, as I think Renee was also commenting about it, we don't have that amount of image, and we have to do other things to make it work. So, well, this was actually the LeNet I was talking to you. They were using filters of 5 by 5, sorry, and they had just a few feature maps. Look here, just 6 at the beginning, and then 16 feature maps as outputs. And that was published in 1998 and was really good to process this MNIST data set. But in total, it had 60,000 parameters, this network. Now, in 2012, you know that it was when we started to talk a lot, much more about convolutional neural networks, because it was the AlexNet. And the AlexNet managed to win the ImageNet challenge, where we have to categorize 1 million images in 100 classes. And they did it. And they reduced the error rate by 10 points. So this is a lot. And if you look at the model, actually, the model is not that different from the standard LeNet. But what they had, well, there were many tricks that they used, actually really smart. But they had, for example, much more feature maps. You see that they went up to 384 here. They used dropout regularization as well in this paper, and they managed to parallelize the training in GPU, what was great because it allowed them to train this model using all the ImageNet data, which was really difficult before. And the network had 60 million parameters, and that was in 2012. And this is the paper by Alex Krzyzewski and co-workers. And if you look at the evolution of the error, this is what I'm telling you. This went down a lot here. And what is nice also to see is what happened with the number of submissions in ImageNet that year that used GPU. So nobody was using GPU before, but then that year we had 4 submissions using GPU, and from then on, we started to have more and more people using GPUs to train. So this talks about the importance of GPUs and computing power in the deep learning revolution, right? So then, well, I mean, I could be all day long talking about different architectures. I'm just giving a few examples here about VGG, for example. VGG, what they managed to do was to create a much deeper network than AlexNet by using really small kernels, using kernels of size 3 by 3 only. And I think since this day, many people use 3 by 3 kernels just as a rule. I actually, whenever I design a network, I use this type of kernels, and I think it's because of the VGG net. So many more parameters, 138 million parameters. And we could keep on talking about it all day long, about the different architectures that we have in convolutional neural networks to solve image classification. But well, if you look at the evolution of the error, we were in like almost overfitting there to the data set, right? Now, I've been talking about how we can use convolutional neural networks to solve classification problems, which are, I think, with the prototypical example of image when we deal with convolutional neural networks. Now, we can do much more than that, and we can solve many problems from computer vision using convolutional neural networks. And one of them is image segmentation. So as I was telling you, what I have to do is to assign a class to every pixel. I had many options to talk about different architectures for doing image segmentation, but I choose to talk about UNet because I'm coming from the medical image computing community, and I think UNet is, it was published actually in MICA in 2015. MICA is the biggest conference in medical image computing. The paper has more than 9,000 citations, and many of the models we developed during these last years are derived from this UNet model. So I think it's a really nice example about how we can perform image segmentation. Let's look at it for a little bit. So let's say I have an image of a brain here, an MRI, and I want to segment this MRI in 4 different classes: background, gray matter, white matter, and CSF, for example. I mean, I could have different labels, whatever. So the UNet is what we call an encoder-decoder architecture, and it's composed of 2 main parts. So the idea of the encoder is really similar to what a standard classification network is, right? We have our input image, and we start using convolutions and max poolings, convolutions and max pooling, max, well, whatever, until I get to this part here that is kind of a bottleneck in this encoder path, right? I reduce the dimensionality of the data a lot. Look at something. Whenever I'm doing a reduction in terms of resolution of the image by using max pooling, what I tend to do is to duplicate the number of feature maps in the output. So I go from 64 feature maps to 128 feature maps and 256 and so on, right? Because it's like what you lose in spatial dimensions, you want to keep it somewhere. But this is just an advice. I mean, it's not something you have to follow. And then we start to reconstruct. We go up again in this path, and we start to reconstruct the original image until I get to the original resolution or something similar to the original resolution. And for that, what we do is to use convolutions and combine them with up convolutions. Now we are going to see what these up convolutions are, but basically are something that try to go from low resolution feature maps to higher resolution feature maps, right? And something that is really important about this network is that you need to put these connections here that are called the skip connections, that what they do is to bring information from the encoding path into the decoding path. If I don't use the skip connections, what I have here, well, it depends on how I train it, but it looks really like an autoencoder for those that are familiar with learning representations. So, and the autoencoder has one of the properties is that it has a bottleneck here, so it compresses all the information there. So if I don't put the skip connections, what is going to happen is I'm going to lose a lot of detail in the output segmentation, right? So it's important to keep the skip connections, and you have different techniques to combine these feature maps with these feature maps. You can sum them, you can concatenate them. There are different things you can do. Okay, so this is the UNet. And once I get the output segmentation map, so what I get is something like this. I get a probabilistic map, right? For every pixel, I will get a probability of being of specific class. And I will do Argmax, and I will have basically my segmentation. So when you train these networks, you can use many different loss functions, but in particular, you could use cross entropy defined at the pixel level, right? Every pixel as if it is a probability distribution, and you compare with the ground truth, and you compute the cross entropy for that. And then you just average across all the images. So how do you implement these up convolutions, that I was telling you, these ones here? There are different ways. So remember that the convolution will take you from here to here, right? It will reduce the size of the feature map. So the transpose convolutions, which are the ones we use in this case, work in the following way. I want to go from here now to here, so from a 4 pixels images to this one, which is much bigger. So there are many different things you can do. One is just to incorporate here some like padding. So you put like garbage information in between, just reach the size that you want to reach after doing the convolution, right? It's an easy idea. You take the image, you add padding here and there, and you just perform the convolution as you always perform. And you hope that the weights you're going to learn are useful to perform this task. Another alternative is just repeat and convolution. It means just take this feature map, perform nearest neighbor interpolation to augment the size of the feature map, and then perform a convolution that will learn to combine this information together. And that's the way in which we implement these things here. Another important thing that I forgot to put in the presentation, actually, but I think it's important to mention, is that these networks are what we call fully convolutional networks. So here, I don't have any fully connected layer in my model, right? And this is important because since I'm using only convolutional layers, I'm learning filters that can be used to process images of any size. So actually, what I could do here is to train the network using, for example, image patches, right? I take patches from my volumes or whatever I'm using in the input. I train my network with that, and then at test time, I can plug a complete full volume image, or a complete, sorry, I'm talking a lot about volumes because I work with volumetric images in medical images, but in this case, it would be the same in 2D. I can train with patches and then perform full image predictions, right? And this is great. And you cannot do that if you have fully connected layers in between, because as soon as I put a fully connected layer, this will fix the size of the input, right? Because I will fix the number of neurons there. So actually, another really famous network for performing semantic segmentation is the fully convolutional FCN, fully convolutional network by Long and co-workers, published, I think, in 2015 in CVPR. But well, I decided to talk to you about this one in particular because it's closer to the medical image community. Since I have, what time is it? Sorry. How many? It's okay, I have to, yeah. So I wanted to comment about some of these applications. So this is, I talk about two applications here, like classification and segmentation. But in my daily research, I use convolutional neural networks to perform many different tasks in this field, in medical image computing. So medical image computing is a really interdisciplinary field where we interact not only doctors, but also physicists, computer scientists, biologists, math, people coming from maths. So, and it's, our aim is to design novel computational methods to extract useful information from the medical images, right? And with a lot of different applications. And I really like to work in this field. I've been working in this field since I started my PhD in 2012, because it's a field where you have really interesting problems that can drive research in, like really, you can develop novel methods that will generalize also sometimes to other problems, but you find really interesting problems there. It's like a really nice pool of problems where you can take and deal with them. So medical images are everywhere. We all have had some medical image at some time in our lives. So for example, X-ray images or CT images, computed tomography images. These are volumetric images, and I work a lot with them, so that's why I was talking a lot about volumes before. These are CTs. Then we can also have, for example, MRIs or images that are not showing structure of our body, but are showing activity in our body, what we call functional images, a PET image, for example. Or we can have also ultrasound, we can have MRI during time. I mean, the variety of images that we have in the medical domain is amazing. And we can find a lot of problems there that actually you won't find in the standard computer vision community, because we deal with volumetric data, because we deal with multimodal data, because we deal with data that has a principled way of being created, right? So when we look at ultrasound images, we know the laws that are making these images, so we can use this knowledge and introduce it in our models. to make them more interesting. So I will talk to you about 4 different applications, or not applications, but 4 different projects, like really briefly, so that then we have time for some questions if you have, that we are trying to solve in my lab in Santa Fe City in Argentina. So one of them is trying to learn useful representations of anatomy. So if we have anatomy, like in this case, we have a CT image of the full body, or in this case, I have a brain image with segmentations corresponding to subcortical structures or whatever. This problem, we usually don't have a lot of data to solve it. So if we try to use standard methods, sometimes they don't work here. So what I'm trying to do is to take advantage of the regularity of these data structures, of these segmentation, sorry, because if you look at the brain, brains are more or less always the same. So you can try to learn representations from there that then you can use to regularize different problems, like, for example, segmentation. If I'm segmenting a particular organ, I know that the organ has to have more or less a given shape. But if I apply standard convolutional networks which have a receptive field that is not that big, it may happen that the network makes bad predictions there. So the representations we are trying to learn, we use autoencoders. I will talk a little bit more in depth about some of these applications on Friday, that we have this Frontiers in Computer Vision panel. So if you are interested in this, you can go there and I will talk a little bit more in detail about it. Another problems are segmentations of lesions, and this is a different problem because here we don't have that regularity that I was telling you before in the organs. If we look, for example, at tumors, tumors are not regular at all, shapes are completely different, and here the type of tools we have to develop are different as well. Or, for example, brain lesions or whatever. Another topic that I really love and in which I've been involved for a couple of years is convolutional neural networks on graphs. So all of what we have been talking about here is the really basic elements and the really basic building blocks to construct neural networks that process structured data, data that is in the Euclidean domain, let's say. So when we go out from there and we leave the images and we go to other structures like graphs, and I try to do a convolution on a graph, it is not that clear how we can do a convolution on a graph. And for that, there are different ways that we can do it, like using spectral convolutions or using spatial convolutions. Actually, people have been building a lot of different ways of performing these convolutions in this field, geometric deep learning, that for those that are interested in this, I recommend this survey by Michael Bronstein and co-workers that is really good and summarizes a lot of work there, in which they have come out with new convolutional models that we can use to process this data. For example, when you have brain activity data, you have it in the form of a graph because you have the different, for example, if you use functional magnetic resonance images and you capture this data, what you will have in general is different areas of the brain, okay, measuring the activation in these areas of the brain, and so every one of these areas can be a node in a graph, and then you look at correlations between that to define signals there. And this gives you at the end a graph with some features. And we want to use, for example, this graph to classify patients whether they have Alzheimer or not, for example, like we did in this paper here, or we have also worked with autism spectrum disorder. I think Guillermo was talking about this in the morning. We go from a completely different approach here, but the idea is to also help to diagnose autism using, in this case, brain signals. And so, well, I'm not going to get into the details of this neither, but I just wanted to tell you that there is a complete field of research there where convolutional neural networks can be used in non-Euclidean domains, like these ones here. And it's really fascinating. And we are doing also work there. And just to finish with another example of what we are doing in our lab, I think this is something really exciting for me. We started to work on this with some of the guys who are here actually a couple of months ago. And it's trying to characterize gender bias when producing medical imaging classifiers. So what we are looking at here is what happens if I train classifiers using a specific databases. In this case, for example, I want to train a classifier to predict among these 8 different classes. And what we were analyzing and what we are actually analyzing is what happened if we use unbalanced data sets in terms of gender. So what happened, because this is something really important that we have to start looking at. There is a complete area of research called gendered innovations. And what they are doing is trying to analyze how gender affects the different area of research in general, right? Going from biology to computer sciences. And we thought about these problems in the case of medical imaging, and we saw that some data sets are highly unbalanced. So we have observed that some data sets have many more images from guys than from women. So what we tried to analyze in this case is, okay, what happened if we train one of these classifiers for diseases using only male, and then we predict on women? Is there a low in performance? Can we see a bias there? Actually, we can, and we are writing a paper about it. And I think this is a really important problem in which we have to work to actually de-bias our model, to create models that even if I train them with a few women images, just female images, just because we couldn't access, I don't know. There are many reasons why data sets are unbalanced. But how we can do, from the algorithmic point of view, to actually create algorithms that can de-bias these models, right? And this is something this is another question we are trying to address in our lab. So for those that want to come and visit our lab, we are in Santa Fe City. It's in Argentina, not far from here, 8 hours by bus, actually. This is our university, Universidad Nacional del Litoral. And this is, well, a campus, you have a swimming pool, whatever. This is a group. We are a lot of people, but this is the Research Institute for Signal Systems and Computational Intelligence. And this is the group of people working with me, actually, my students and collaborators. Some of them are here, some of them not. So with this, I think I can conclude the talk and open for questions. Thank you.
Okay, who has some questions from the audience?
Here, this.
Okay.
So is there any advantage of using max pooling to reduce the feature map size instead of strided convolutions or non-padded convolutions, for example?
Well, this is a design choice, kind of. I mean, when you use strided convolutions, you are basically learning the pooling operation, right? Because strided convolutions is, for example, if I use a convolution with a stride of 2 and a kernel size of 2 by 2. So this will be learning the pooling operation. I don't know. I mean, in general, I use max poolings. It may be some study there showing some differences, but I'm not aware about it. I mean, in general, when you design the network, I particularly use max poolings. But yeah, in this case, what you would be doing is learning the filter. Yeah.
Question.
Thank you, Enzo, for the talk. It was really nice. Regarding the convolutional neural networks on graphs, you show a matrix, a correlation matrix between features, I guess.
Yeah.
What about using, for example, a sample by sample similarity, like a reproducing kernel Hubel space, for example, as a adjacency matrix? I mean, not feature by feature, but for example, sample by sample or whatever is. What's your opinion?
Yeah, I mean, this is a bit confusing. I think the image I'm showing because I didn't go in the details here. In this case, I mean, when you do graph convolutions for medical image analysis, in general, we go in 2 directions. So one of the directions is if you construct the graph as a population graph. So your graph, every node will represent a patient, for example. And you have labels for some of these patients, but for some of these patients you don't have. And you are kind of in a transductive setting, like the Khipu paper, maybe you know, 2016, I think, ICML. And in this case, your graph represents your complete population. So the features that you put in your graph, in this case, will be some descriptors of every patient, right? And connections may be related to, I don't know, genotypic information or phenotypic information or similarities shared from every patient with the other patient. This is one of the models. And then you train this network using always the same graph, and you predict for those nodes for which you don't know the labels. But when you compute the loss function, you only use, of course, the data that you have labeled, right? But the graph is complete, and you have in the same graph your training and test samples, kind of. This is one of the settings. The other setting is where every graph, we call it individual graphs, where every graph represents a patient. And so here is this case in which we have this is for fMRI data, so functional magnetic resonance images, resting state, actually. So these are captured when the person is doing nothing, just sitting in the machine. And what we do here is we construct what are called connectomes. So a connectome is basically a graph where you have different parts of the brain, right? And every part of the brain is a node. And the connections between the nodes are related to correlations between the different areas. And that's the way this matrix is constructed here. So it's like you have two different views for this. And these open two different problems. In this case, for example, we use graph convolutions to do metric learning. So metric learning is when you want to compare two different graphs, right? And get a number. And this number should be something like a metric, so it should be low when you have similar graphs. For some reason, they are similar. Here we were using, for example, to learn to compare patients, healthy patients, or patients with autism spectrum disorder. So for this, what we proposed was to do like a Siamese network that takes the graphs and produces a simple output. Whenever you deal with graphs, you have like these two models, and depending on the problems you're trying to solve, well, you will put wherever is of interest for you in these connections. So they are designed depending on the problem. So that's.
Thank you.
Question over there from René, I think.
Yes.
So regarding the use of UNet, the architecture seems fairly similar to SegNet. It appears the main difference is the skip connections, but I was wondering first whether you could comment on that. The second one is what type of data is used to train them, given the lack of segmentations for brains, I guess. And so I guess one approach is to just use computer vision data to pre-train. The other one is maybe to use data augmentation with GANs. So commenting a little bit more on the challenges of dealing with lack of ground truth segmentations to get the results.
So regarding the first question, I think you are right. I mean, they are pretty similar, both architectures. But regarding the second one, which I think is a really important point for the complete medical image computing community, so yeah, it's true. For example, sometimes when you want to train these segmentations for the different tissues in the brain, we have like 20 images labeled. I don't know, something like that. One of the advantages at the same time of medical imaging is the regularity I was telling before. Because here, I mean, it's different from an image from the wild, where you have a lot of variations, and medical images are captured in a really controlled setting. So if you put all your brains, like brains from different people, and you put them like overlapping them, and you can actually, if you want, register them or whatever, they will look really similar. So we are actually taking advantage of this regularity to train these models. So for example, one of my research projects with some of the students here is about trying to learn like lower dimensional representations of the complete brain that then I can use to regularize the segmentation process and get segmentations that actually look like a brain. I mean, if I compare in a lower dimensional space, I can constrain the segmentation process with something is called anatomically constrained neural networks. I don't know if you read this paper. It's a paper that we published in 2017 by Ozen Oktay and other people. And there we are trying to use the few images we have to learn some representation for the segmentations, and then use this kind of constraint to constrain the training process so that the segmentations we produce are not only good pixel level prediction, but also putting like a global image of what we are predicting. And that works. This is one way, for example, in which we can tackle this problem, like trying to take advantage of the regularity of the medical imaging. At the same time, if you train one of these networks with, I don't know, 20 images, you will get some. I mean, I was really surprised when I started with this, and I trained my first segmentation algorithms for anatomical structures, that the results are not that, I mean, that's not as bad as you would imagine for having only 20 images. The point is, you always have segmentation, like spurious segmentations and things like that, that you will try to remove, or my research, I mean, one of the things I'm doing is this, trying to remove all these things by producing anatomically plausible segmentations, segmentations that live in the space of anatomically plausible masks. And this is one of the ways you can try to tackle this problem. Yes, so.
And on that same note, it is true that there is a lot of regularity and that maybe 90% of the brain look the same. But when it comes to disease, the variations due to disease are the ones that matter, and we want to detect those specifically. And so if I have a metric just evaluating quality of segmentation, I will probably not see much of a difference. But for the disease, it will make a difference.
Yeah, exactly. So in these cases, what we try to do is to have in our data set some cases where there is like pathological cases as well. But yeah, it's true that the regularities, depending on the pathology you are looking at, but yeah, what I talk about regularities when I compare, for example, anatomical segmentation with lesion segmentation. Lesions are completely, the structure of the lesions is completely different from one to the other. But yeah, you have to be careful about what you are saying, having in your data set at least some examples of data with pathology. Yeah.
Cool. We have a question from the internet, from somewhere in the world. I think it's quite interesting. So the question is, imagine you have video classification, something like that, where you have a 2-dimensional image, but you also have a third temporal axis. What are the advantages and like problems of using an RNN plus an RNN on the temporal scale plus a convolutional network on the spatial axis versus using 3D convolutions?
Okay. So wait, let me get the question again. So
yes.
You say you have images that are 2D, but this is a sequence of 2D images.
You're doing video classification, for example.
Video classification, yeah. And you could use there like spatial-temporal convolutions, you mean? Like convolutions that move in the space, but also in time.
Yeah.
These compare with 3D convolution. But
So
basically, you would implement it as a 3D convolution, actually.
So that's one thing, like having a 3D convolution, and the other one is just having an RNN that has a COMNET in the input to hidden mapping, for example, and a hidden to output mapping. That's a COMNET. So like a COMNET STM. Well, sort of.
Again,
yeah, so you could also have an RNN where the input to hidden is a 2D convolutional neural network.
Yeah.
And the hidden to output is also a 2D convolutional neural network. So basically, like an RNN that on the temporal scale and on each individual.
Yeah, I mean, I haven't worked a lot in video actually. So I mean, yeah, using RNNs would be a good solution there, I guess. What we have done are some comparisons between using like independent 2D convolutions and 3D convolutions. For example, when you process not temporal data but volumetric data. Okay. And in this case, when you have volumetric data, it's always better to use 3D convolutions because they incorporate information from the context, not only from the given slides, but also from the other slides. So this is what I can comment on that. But not, I haven't worked much with temporal data, yeah.
Any more questions? Okay, since we have 2 minutes left, I will ask one. So in segmentation, you're using just the sum of cross entropies over pixels, which is essentially equivalent to doing maximum likelihood estimation and assuming that the distribution of the output image condition on the features is independent for each feature, right? And I know, at least in the past, people use conditional random fields to avoid doing this kind of independence assumption between of the pixels condition on the features. Do you think that's relevant, or as we get like more and better and bigger networks, these things are gonna be in disuse and just maximum likelihood estimation with like standard cross entropy is gonna dominate?
No, yeah, I think it's a totally valid question, and it's actually a point in which I'm working a little bit. So in general, when you see this, if you see in the last years, what people have been doing is using a standard convolutional network like this with pixel level predictions, and then applying a CRF on top of that, so that you get like homogeneity, kind of trying to join regions that are similar in terms of homogeneity. However, this has the problem you are saying, and these are all pixel level predictions that I'm using. For example, also I can use, for example, a dice loss, which is a loss based on the dice coefficient, but this will also look at the pixel level prediction. So what we are trying to do with this representation, in case of anatomy, we are trying to learn these lower dimensional representations that have global information, so that we don't need to expand the receptive field of the network to the complete image, but we can use these representations that we just learn using autoencoders. So we use autoencoders to learn these representations that are global, and then you use this during training to encourage the segmentations to go towards this space. Or also you can use it as a post-processing step. Actually, this year we had a paper at MICAI about it, like using convolutional, like autoencoders to learn representations, and then you take one segmentation, any segmentation of the, let's say you are segmenting the lungs. So you take the segmentation that you produce with any classifier. It could be a neural network, it could be a random forest, wherever you have a pretty bad segmentation if you want, but you project it to the manifold that you learn, and you reconstruct it uses to your convolutional autoencoder, and you will go back to something that looks at least like a lung. And these are all ways of incorporating kind of global clues into the results.
Awesome.